I'll unblur my background. I'm in the messy room. So what we got to last week, we were talking about energy can't be created or destroyed, but we can convert from one form into another. And in terms of a battery, we said a battery was like this source of chemical energy, but we're really saying it's a storage of electrons. And if we can get electrons to start moving in a circuit or in a loop, that they have an energy, if we have an energy source, a continuous loop and a conductor or materials that allow electricity to go through it, as opposed to static that doesn't allow, like plastics don't allow electricity to go through it. So again, if I was back here starting, I'd say, right, I've got my wires there going around. I have at the end, like I've attached here just to show you. I'm going to attach a little light emitting diode, a little LED light bulb, and then I'm going to see, right, so what I might ask the students is, right, it's not lighting. What's the problem that it's not lighting up? And hopefully they'll say to me, well, it's not in a continuous loop or attached to the other side. So you can see straight away when I attach it in the continuous. So I have an energy source, I have conductors to carry that, and it's in a continuous loop, and the light bulb comes on. The one thing that I'm going to mention, nearly every kit now comes with, as opposed to the old-fashioned filament bulbs, they all come with LED light bulbs. And it's in the notes, and it is in the notes, but an LED has a long leg and a short leg, or it has a positive end and a negative end. So it matters what way you connect them. So if I was to, and to be honest, for students, I just, especially in primary, I'd probably just say to them, looks like the batteries and remote control. So if I connect that way, the light bulb is not coming on because I have the plus and minus the wrong way around. So if you were demoing that, maybe just, just get the long leg goes to the negative. We have the long, I'm not going to say it now when I look at it. So just with an LED light bulb, it has a long leg, a long wire comes down, a shorter one. And because of that, you have to make sure the plus goes to the plus and the minus to the minus. So there we go. We have our continuous loop. If a gap came, like in the fetus field, if a gap came in the circuit, so now I don't, and remember that was in the notes, it's no longer in a continuous loop. And when that happens, the light bulb is not going to come on. But if I close the gap, I can see the light bulb coming on. If I open the gap, the reason that it doesn't is that the electrons can't get from there, they can't jump over to there. So I wonder if I put some, this is a really good one to do with class with your kids, right? So if I put something into the gap, would the light bulb come on? So I'm going to put a piece of paper, and you would say, do you think, so again, like you're not saying, oh, I'll put a piece, you're saying, well, what do you think? Do you think the light bulb would come on? And I've got my energy source, I have it in a continuous loop, but I've put a piece of paper in there and no, the light bulb didn't come on. So I might try different materials. I'm going to try, just because I have it here, look, I'm going to try, actually I'll do one you might see quicker. So I'm going to try maybe a piece of tin foil or a little bit of a coin or something I could try. So again, I have that gap in the circuit. I'm going to see what I can put in the gap. And there, look, I'm putting in a piece of tin foil. Again, you would get students do this themselves because you have enough kits, but do they think the light bulb will come on? And yes, it does. So what I'm finding out is whatever the material that tin foil is made of allowed the electrons to go through. The paper blocked the electrons from going through. And hopefully what we would know, look, if I even do, I'll do one more for you. I'm going to put in a coin. So what do you think will happen if I close the gap? Will the light bulb come on? And what you can see, yet the coin allowed it to come on. What I was really trying to demonstrate there, what that's doing is testing for conductors and insulators, but not using the word testing for conductors or insulators. It's using that inquiry-based approach again to see, did some materials allow the light bulb to come on? Other materials didn't allow it to come on, but then we can start dividing them into, they can group them together into which ones allow the light bulb to come on, and eventually end up with what they must be, like we call them a conductor or an insulator. And just because it's in the notes, I'm going to show you then. So what if I took, I'm going to take a piece of paper, and just an example, I'm going to try and get something that I can control the light bulb coming on and off. So I'm going to take a piece of paper there. And connecting that at this side. And I'm going to put, when I have a look. Even look, I'm going to put it in this way. So what we can, look, I have that. Even if you can see, it's terrible doing this on screen. If you're in the classroom, you'd see it perfect. Right, I have it in, I have that, I have a piece of tin foil, but I have a bit of paper and I have another bit of tin foil. And hopefully what you'll see is every time I press the tin foil down, look, when I connect the two of them, I've closed the gap fully and it comes on and off. And what I've actually made is a little switch to control my circuit. So in a very straightforward way, we've looked at conductors and insulators, but also designed a switch from everyday materials. Now I did that went through that really, really quickly there. It's in the notes, it's in a lesson plan step by step to show you that. So it's really, that's just about.
Looks scary. That looks scary. These only female ones. These are only female ones. Crocodiles.
Hello. So sorry, just I think someone was speaking there. What we're going to, which I've lost it, yeah. So you can see it's just building up those concepts around electricity, just to make sure all the basics are done. So I'm going to go back now, and I was saying, in that case, we used a battery as an energy source. Do you remember last week I looked at and these will be in your kits as well, the solar panel. So every time the light hits, every time the light hits the panel, it converts from light energy to electrical energy and the light bulb comes on again. How do I know? Because I'll see the light bulb coming on when the light hits it. Then the other one we looked, and this is the one I want to get to for today that's really important. I'm looking at, and again, look, I'm not even going to use the terminology, and I think I really quickly did this last week, so I'm going back to it now. What I have is a thing that probably to students or to any of us looks like a little motor, and it is a motor. It's a motor when I connect an energy source to it. But what I mentioned to you last week is if I get that little spindle on the motor and I spin it, see that? I spin it really quickly by hand. What happens is every time I spin that, it's producing electrons because it's producing electrons, and those electrons are being converted into electrical energy. Even if I forgot about, right? Even if you started here and I forgot about electrons, well, go back to saying, right, we know that for electricity to work or for a light bulb to come on, we needed an energy source. We needed to be in a continuous loop, and we needed conductors to carry that energy source. So this thing, for some reason, every time I spin it really quickly, is causing the light bulb to come on. So it must be an energy source, is what I can say. And hopefully there you could ask the question to the students, say, well, what if I could keep that thing, like spinning it by hand and a light bulb comes on isn't very efficient. So what if I could keep it spinning and keep it spinning for a long time? So again, I'm going to put this one on here. So I have a little, you'll have to ignore me for a minute. I have a little fan. I have a little fan there that I put on it. And what I'm going to do is going to try and get the fan to spin. So if you were outside, you could try this, but because we're inside, I'm going to have a hairdryer ready to go. So I'm going to put the hairdryer and hopefully you can see. I'll go again now, right? When the hairdryer is spinning the fan, the light bulb was coming on. We just have a look at it again. So what we were managing to do there is we were connecting. So this little tiny device there is actually like a mini little wind turbine, a tiny little wind turbine. I would have it. I'm going to go because that's where we're going right into wind turbines today. I think I showed you this one last week, and some of the engineers when they come in to visit you will have these, right? And it's brilliant, and we're going to have a look at it in a minute. But students would expect that to work. They expect that that's going to do something. This is so much better for the learning because you're getting down to the nitty gritty, like the little basics of it. So every time we have this device spinning, every time we manage to keep that spinning, the light bulb turned on. if you, like if I just spin it by hand there, just so I can demo that to you, the light bulb isn't coming on. And the reason for that is spinning the little fan hair by hand doesn't give enough kind of pressure on it. It needs the hair dryer, or it needs that, like that spin, me giving it a quick spin like that. So either the hair dryer or just doing it by hand won't actually generate enough electricity. So what we've done there is like we've established that how does electricity flow, different sorts of energy sources, and hopefully what we're starting to move into here then is that in this case, if I can keep this moving, I have a never-ending cycle of electrical energy. Like it's not, unless like the little generator here breaks down or something, once the wind would hit that, I'm going to be able to keep my light bulbs on. So really the question is, how can I keep that how could I design something to keep this turning really, really well? And I don't, because they haven't, you're in the kits, you're getting, it's sort of a bigger version. It's somewhere between looking like this one and a bigger version of the, just a little motor I showed you, because it shows the gears and stuff inside of it, right? So I think, as I said, if I take off the blades for this is the science bit, right? Every time that that's turning there, every time that that's turning, electricity is being produced. The engineering bit is, well, how do I design to keep those blades turning? How do I come up with a design that keeps those turning really, really well? So in some respects, like with your students, that's why I said, do you remember last week I was saying we've got the 5 stages to engage, explain, explore. It kind of doesn't matter where you start, because you go right into an engineering challenge and come back to that if you wanted to do it that way. So it's up to you where you feel comfortable starting at it. Like you could literally do that little demo and say, like, something's like spinning this is getting electricity to produce. And I guarantee you someone in your class will come up with saying, well, how would we keep that turning? You know, it's the questions we ask that kind of prompts the better discussions. So our bit for today then, what we're going to take a look at is how are we going to efficiently design a set of turbine blades, or little mini wind turbines, but then connect them to a hub that has a generator to see are we connecting electricity. If you've completed the earlier part and you've carried out all the little circuits and stuff, well, then the students should have, like, they should be fairly good on the electricity and making circuits bit. And if you haven't done that, if you jump straight into the turbines and do the turbine design, that's fine too. You might just go back and do the electricity parts, the little prototypes and stuff another time. Now I'm going to, it was just our recap witness. I just want to share for a minute. I have so many tabs open at the moment. Oh, here we go. So this is what we're looking at, is the second part of this. It's the hands-on approach to understanding wind power. So a little bit like last week. So these are here to support you. This PowerPoint and stuff is here to support you in the classroom. So we're exploring wind energy by looking at from past technologies to modern solutions that we have for our energy. Again, they're just a basis of what we'll be covering in this section. And the lessons are all curriculum linked as well. I just haven't put them in there. I'll fly through this. The recap here, or if you haven't covered this bit again, it's just a reminder that energy cannot be created or destroyed. We can convert from one form to another. Kinetic energy is energy that's moving, energy that's in motion. Mechanical energy is like mechanical energy is the motion of an object, I suppose, in terms of like a turbine, or when I was mechanically turning those blades or spinning the blades. Mechanical energy is a form of kinetic energy. Electrical energy is produced when electrons move through a conductor, such as through a wire. So we really looked at electric energy, and really what we're moving towards now is like, where can we get green electrons that are renewable, or not going to cause pollution by producing them. So that's just the back. Yeah. what exactly is wind power? So wind is just air in motion. So it's created by the uneven heating of the Earth's surface. Daytime, the sun heats the air over the land faster than over the water. There's a description of it there if you want to go into it. Why is wind a renewable source of energy? Because it's driven by natural and ongoing processes of the planet. So as long as the sun hits the Earth, we're going to be producing wind. And then unlike fossil fuels, even if you didn't want to do that, or like they're unlike like fossil fuels, the burning of coal, even if we leave out the pollution part of burning of coal and oil, they will eventually run out because we deplete them quicker than they can be replenished. So renewable sources like wind, solar and hydro are constantly being replenished, making them suitable for the future or renewable energy source. Without a doubt, there comes criticism, and I'll just point out now, like battery production, the waste that's involved, even producing turbines or making solar panels. But the waste or the parts of them that gets criticism for it, like the clean energy source that comes from it far outweighs that. And then as technology improves, that those processes will improve also. I think it's probably our battery production we need to cut down on the most, to be honest. So what about wind energy? So if you even forget like that, like a little bit for the students, well, is this something new, like that we started to produce or using wind turbines and getting energy that way? No, like from ancient times all the way up to modern wind turbines, it's people have used like harnessed the power or the energy from the wind. So windmills back like 1,000 years ago for grinding water and pumping water. So in terms of like the engineering piece, they were still doing that. They were using the wind, like they were using the wind to take wind energy, that kinetic energy, and get it to move something to perform a task. What we're looking at is how do we get it to move to drive a generator to produce electrons. That's the difference. So we're trying to figure out, well, how did they come around doing that? So you just see a little nice picture of like how it evolved. And then what's so special about, like what's so special about a wind turbine? What do they actually look like? And I think this is really important for us. So generally they have 3 blades. Apparently, and I could be corrected on this because it's a long time since I've looked at it. Apparently 2 blades is even more efficient, but 2 blades create a huge amount of noise when they're rotating. So 3 blades is really efficient, but minimizes the noise pollution. So that could be something for students to have a look at themselves. Then they have the blades, they have the tower, the big tower that produces supports the turbine structure and drives electricity into the grid or wherever it's going. And the nacelle then is the longer part you see that has the main, like the generator is in there, the shaft, the rotator that turns the blades, that turns that generator. It has an animator to kind of detect the wind speed so they can slow down or move around to capture the wind and protect it from lightning as well. So that's the kind of the basic structure of the wind turbine. And this is what we want to really get to, like, how do they work? So in that picture there, without me describing it, see the electric generator. That's what I was showing you, the mini one that I was just twisting by my hand. So that's exactly what that is. The difference in a wind turbine and in the kit that you'll get is if I put a gear system to that, basically the gear system will speed up the rotation of that electric generator. The quicker I can get that moving, the more electrons I start to be able to produce. So doing it by hand, I have to kind of really push it, where if I have it on a gear system, what are gears designed to do? Speed something up or to slow it down. So in that design within the nacelle is the gear system and the electric generator. So if you think about it, we're back to these energy transformations. We're using the power of the wind to turn to mechanically turn the blades, which turns the gear, which then turns the generator. So it's exactly like what we demoed, what I just demoed to you with the little motor, except it's just a little bit more sophisticated doing it. Like it's a nice design and it's refined and, it's in a nice structure. It's a little bit more than that, but I suppose the science of it or the engineering of it is the same. Now, this is the bit. This I'm gonna stop sharing for a second, and I want to bring me back here. I want to show you before we go into this, because this forces and things moving can get complicated, right? And can get a bit, everyone else, I hate talking about forces and lift and drag and stuff like that. So the first thing I'd say is if you got students, if you had a big huge sheet of paper, right? Or if you go outside on a windy day with a sheet of paper like this, and I'm holding the sheet of paper like that, and I walk towards the wind, well, I'm going to feel the resistance of the sheet. Like if it was a big sheet of paper, but even walking like that, I'm going to feel it. If I turn the paper that way, no, I'm not going to feel it, because there's not as much surface area to have a resistance or have a drag happening. So even like if you have your hand out, you feel like in the wind, you feel the resistance. You turn it that way, there's less air resistance or less drag that's going to happen. The second part about lift, well, how do we get them to do, like, how do they actually turn? And I don't know if you are watching, this is a good example to give a demo. I've just taken a little sheet of paper, and I don't think it matters. I'll cut another bit. I just cut a strip from an A4. And I think this is the best description, the best way you can do this to explain it. So I'm going to take a little sheet of paper, and if I was to blow air across the top of that sheet of paper, do you think, will it just go down? Like if I start blowing on that, or the wind blows on it, will it go down, or what do you think would happen? And like that's where, if you ask the question, I suppose a good way to start. So when I blow air across the sheet of the paper, actually what happens is, if you notice, it's lifting up, it's not going down. Look. So it actually causes a lift when I blow air across the sheet of paper. And I'm going to go back and explain to you. I'm going to use the image to explain that. So what we can see, right? So where I was blown across the sheet of paper had fast moving air, like I was blown on. So the air was really, really fast where I was blown across that. And actually what happens is, it's just called Bernoulli's principle, but what happens is that fast moving air causes low pressure. So it's moving really fast, but it causes low pressure. And then basically what happens, okay, I went. Am I back? Yes. Yes, thank you. Sorry, do you know what happened? My laptop, I moved from my office up here, and I forgot to plug in the laptop. What was I in the middle of explaining? Right at the bit that nobody likes. We'll go back to it. The fast moving air causes low pressure, right? So it's like Newton's law says, for every action, there's an equal but opposite reaction. If there's low pressure on the top, that causes the air underneath to be slower moving, which actually causes a high pressure. And that's what lifts the wing up. That's how birds or an airplane or anything goes. So over the surface of the wing, you've got this fast moving air. Underneath that, then you've got slower moving air, which actually, so it's kind of the opposite to what you would expect, that you'd expect the fast moving air to be fast pressure. So it's that slow moving air is actually what causes high pressure, and that gives the wing a lift. That causes it to lift up. Do you see there? You see even on the diagram that you have there, you see the end of it where the tip of the wing is really pointed and it goes into that point. That even that little design, that little aerodynamic design on that causes the air to move really, really fast, just because of the tip, the way it goes in, which causes the air underneath it to be slower and even more high pressure. So if you ever notice, like that's why Formula One cars really go down into that dip at the back. And you'd see a lot of cyclists with the helmet, you know, the one that kind of goes into like a little point at the back. Really professional cyclists often have it on, and that's because it's maximizing this Bernoulli's principle to have more of a lift and less drag happening. Now, you could totally leave that out, right? You could, like, if you don't want to talk about that, you could just literally say that in order for us to get like the wind turbine blades, or for things to fly, you have to have lift. So that's the explanation of lift. So drag is kind of drag is the resistance. So drag is what's going against that to stop it, like when the air, like what we said, like if I was running outside. So you've got the two of them like working against. You've lift trying to get it up, and you've drag trying to get it to slow it down. So turbine blades are designed to create more lift and minimize drag. So the design and the angle is really, really important. So blades are designed exactly that. So the blades are they're designed like airplane wings to maximize lift and reduce drag. So it's no different, right? It's absolutely. So I'm gonna actually stop sharing and go back here for a second. That's absolutely no different than if I come back to this one and have a look, right? So what we're saying is that the blade design is designed to maximize lift and minimize drag. So the obvious one, now you'll have the demo one in your class for this, right? So that's where you could even start. If I have that turbine sitting there, and I wonder, it'll probably spin now because it won't. I'll try the hair dryer. You see, it wasn't budging with the hair dryer, and the reason for that was that all the air that was hitting it was just causing drag or air resistance, because it was literally just hitting off the blades. So blades need to be designed or turned in a way that they're catching the air going over them, so that we get that fast moving air. So they generally don't hit the air full on. They turned at an angle to just kind of play with the air, is the way I would say it. If I turn them this way. Now, I'm not going to help matters because I have two different types of blade designs on this, so I don't think it'll catch anything. They'll cancel each other out. And then hopefully you'd see that the blades started to turn. So really what you want to do a demo. And this one we're going to go into the demo model. I'll start there for a second, right? What you have coming in the kits, you've got these little hubs. So that's like that's going to sit on the nacelle of a turbine, basically. You've got little hubs like this. They're like, you could make this without having a hub like this, and you could use recycled materials, but they're just, I know they're kind of designed to work really well, and they're easier for students to work with. They have six little holes through it to hold the blades on them, and then there's a little hole in the center that will attach directly onto the turbine that you have. So what we did in the kits, I think there's 10 of those that comes on one main turbine. So basically what that's going to allow that the students can, like maybe working in two, or if you're bigger class working in groups of 3, they can work together to design a set of turbine blades. So then can be tested for electricity. So the first part of this is, I'm going to explain it step by step and then wrap it all up together, how it makes sense. So there's my one. I think I showed you last week that I came up with the design. Okay, so that's literally just using this hub and some like paper and card. Now the only thing I don't think that we supplied in the kits. It always is the card, and it's literally just like construction card, like every day. But I don't think paper. I don't think if you use paper, I don't think it would be strong enough. So I definitely recommend using card or any other materials you might find around. But so just to show you, like it's literally just that like everyday kind of construction card used there. So you have your hub. What you also then, what every little hub pack comes with, and I'm using wooden skewers, but yours are different. But just to show you, I'm using wooden skewers, but in the kits that you'll have they're little aluminium, like they're steel connectors, so you can reuse them a lot of times and they won't break when the students are working with. So you've got a main little aluminium hub for the center of it, and then you have for each of the blade design, right? So what happens, I don't want to take them all apart because then I won't be able to demo you, right? So each little kind of starter kit or prototype before there's any design on it has the little hub with the 6, like the turbine hub, and pieces of corrugate card, the corrugate card with the holes in it. What I would say to you is that you've got pieces of those to hub, and then you've the metal parts to connect it. And basically they're kind of, even if the students designed, you could let them bring them home, but I'd be recommending that that's what you would hold on to do to do these again next year, to keep them in, like to continue it with a different class. So where you can start within your kit then, I didn't bring it up. Sorry, I wanted to demo, right? Where you start, I have some here, I can show you. And there's picture guides and stuff in the lesson plans for this, so it makes it easier. So I'm going to go through the technical step by step, and then I'll just show you how you could present it to the students, right? So where you could start is make a little, I've only the wooden skewers, as I said, right? You could just, using the little metal components go into, I might take that one apart, sorry. So as I said, now I'm using stick here for a second, right? The metal part goes into a little bit of corrugate card, and then basically your demo one in your class, you could have that made with just 6 of the little pieces of corrugate card. Like you'll see it in the kit, you'd have the 6 little corrugate cards as your turbine sitting onto your hub, and demoing to the students like that. Basically it's the structure of a wind turbine, but it's not very efficient. Like the blade designs are very basic, like all right, they might catch the wind and stuff, but they're not really going to be designed in a way, well, one, they won't look good aesthetically, which is important, but also they're not going to be designed in a way that maximizes that lift and drag that we talked about. So if I had all the pieces here, I made them into it, and I take another one off to show you like that. Basically, look, you'd have 6 of them, like just as a prototype, the little piece of corrugate card, and then demo to the students like what it looks like there. So their first challenge is they're going to design a set of wind turbine blades that are designed in a way to be really efficient to spin the generator and see can you produce electricity. What I would do, right, if you look, this is where your class better than anyone, so you know what way to do this. I would personally, if it was me, I'd limit the size that the blades can be. So particularly if there were younger classes, if those blades get really, really long, because it's like, I know we're saying like try stuff and test stuff out, but there's a limit to what it can work at as well. So if they got really long, they tend not to spin very quickly. They tend to kind of just get a lot of drag. So the way and like if you're doing a good STEM challenge, you'd always put like, certain conditions and parameters on it. So I would kind of say if they can't be any longer than the A4 sheet, so they can use their A4 sheet in whatever way they want, but the blades can't be any longer than that. Width-wise, they can decide themselves. That's up to themselves. They could do, and they mightn't work very efficiently, but that's like, let them try it and test it. what I have found, right, what I tend to do, you know, the way we were saying, like lift and drag, I could just, like say, I'll even cut that in half, right? I'm going to cut that in half, a piece of A4. Now this, look, I'm going to cut two different blade designs here, right? I'm going to go with one with a pointy tip on it, and one just kind of rectangular. What I could do is literally just stick them to the back of the corrugate card like we showed before. So I could just literally stick them on. And it will work. It will work, right? So I can like just stick it on a piece like that. And then if I had the proper bits now to connect it, and then attach, or here I'll use this one. Look, it's like I could literally just stick that onto that, right? And I like it will work. There's not a bother. But I have found, because it's the back of it then will have like resistance, the way it's not doubled over. So what I found is just a tip. I tend to, so if I'm doing like, just I'm doing a rectangular shape, I fold the paper in half. So that my blade structure, it's kind of like it's doubled over what's at the front and the back. And then I stick that into it like somewhere. So I'm going to even show you. Look, I'm going to. So what I put on the front, I put on the back, basically. You could use a bit of Pritt stick even. Look, so I fold that into it like that. And I'd want to seal up along the side there as well. So even a little bit of Pritt stick would do that. Now, I'm going to just use a little bit of Pritt stick and I seal up along the side. So you're kind of nearly on into a construction or an art lesson, even when to decide on their blades, to design them. It's more aerofoil, like what we were talking about. It's more gone into like a kind of three-dimensional structure to do it that way. So it's still, all I'm doing is the one sheet of paper, like an A4 that I've cut in half, and then I put it into a quarter to make more of an aerofoil shaped blade. I just, then that goes, look where the little corrugate is. That goes into the blade like that, right? That attaches. And what I'd have is I can move that then. So they can twist, you can turn them at an angle. Because if I have the wind blowing straight at it like that, it mightn't work very effectively. I can turn them like that. You can experiment with turning the blades. I think what I'll do is I'm going to give you the lesson plan that shows you the two versions, that you're just cutting out the blades like with the cardboard and sticking it onto it. And I'm going to just show you where I've doubled it up to have more. I just found the structure, it spins better and stuff. So when the students, like, so my one I did, that was the design. So I took, like, you know, you could give them time to design them and make them look aesthetically and look nice, or color them in and stuff as well, and experiment with the blade design. So if you had 3 students working, they're working on a set of, and actually I put in 6 blades. So you could decide to only do, the students might decide to do 3 blades, or make 6 blades and then test to see which is more efficient. So as we were talking about, look, you can turn, if you were bringing them outside now, you can turn the blades and stuff to have a look at the, like, to see which one catches the wind, because you're going to have the aluminium, the little aluminium bits that go in there. It's much stronger when you if you were to take them outside, or you're even having a hairdryer. The little wooden skewers work really well, but I find they can break a little bit if there's too much wind. So from your point of view, the metal ones are just going to be much stronger in doing it like that, right? So if you could have like a class set of them, but you'll only have one generator to test it on. So rather than them going to waste, what I would suggest, and you'll see that in the lesson plan, is, well, you can still test these before they actually test them for electricity. So if I just put in a long skewer, a wooden skewer there at the back of that, look, see, I can have a wooden skewer there. What I also made then, I took an old Pringle can, or any, I think that's a Pringle can of some sort of, you could take a 2-liter bottle or anything. And in the end of it, I put some stones from out in the garden, or I just put, even if you had a 2-liter bottle, I put a bit of water or something in it to weigh it down, because it'll turn over. And on the top of that, there's a little piece of straw there on the top of it, and you can pop the turbine through there. And if I was to take it outside, I can just test those turbines like that, right? Before I'm even, because that's testing what we're talking about, the mechanical turning of them, right? So using the wind to mechanically turn them. The other bit is then connecting that to produce electricity, but we need to be thinking of the two parts, like we need to look at both parts. If you're making that, so if you've that right, and it's kind of, and like, do you know what, there'd be a lovely classroom display as well on top of it. So you see at the back of that, see the way that can move, like that's just going to fall off. So you need to, I'd either put a little elastic band there, or you could get, I find a little elastic band is ideal there, or even actually the sellotape won't work, I'd need too much of it. You just want to put something to stop that. You want it to be able to move, but not be able to come. Actually, the tape worked there, look. And then, no, it didn't. You did it, yeah. Now it is kind of working. It's still allowing it to move. A little elastic band would have been ideal there, and I can see that that's kind of weighing, like it's pushing forward a little bit. So I'm going to put a little bit of tape and to hold it down, like that. Now, what I could do, I did mention to you guys, and I'm happy to do that as part of this project sometime, like during Science Week or the week after. I would be happy to come and do a Zoom, like a group Zoom, if you wanted me to demo the making of one or something like that, to kind of go through that part of it, or to go through the electrical component of it. If, like, look, we can follow up and discuss that. The best thing here with this, it's not, even if you make them this way, right, that's just to kind of really cut out some shapes, attach them to the pieces of corrugate card and add them on, they'll still work. It's just, look, you can see yourself, like the structure of that is just not as like solid, like it's just not, like that just gives it a better structure, like that's going to be like, it's just not as strong. So this just makes it a better structure to work with, so you're going to have more success. But like, as I said, that's totally up to yourself. You could design them keeping a basic look. There's some that I just made, they were just purely rectangular. So if there were a younger group of students and you felt the kind of blade shapes and different designs was too much, you could just actually get them to do rectangular designs, but make them look really nice, but they can still turn the blades and pitch them. Now, you know, there's still a lot of learning in that to see how do they come up with the best design. Maybe like if an older group, you'd probably be going into like that they have the piece of paper that they folded in half, but they can come up with whatever design that they want from it. Like that's up to themselves to design. So that's where, sorry, it's in the chat. That's where it's up. That's where it's up to yourself. Like it's up to you guys, how far you take it. Like if you want to up the design on it, or you want to, even for the first year, if you only want to keep it like that, you had a few shapes cut out in advance and allow the students to work with it that way. There's still a learning part in it. When they have finished, I don't have the exact kit that you're getting, right? But basically what you can do then, when the students have finished their turbine design and maybe checked it outside, what you can do is, in the wind turbine that you have as a class demo, it's not exactly like this one, but basically what you can do is attach the students different designs to it, and either go outside or use the hairdryer and see, are they generating electricity. So probably in the primary classroom, the easiest way to do that is the light bulb turning on? Like, are we producing electricity? Is the light bulb turning on? And how long does it take for the light bulb to come on? I don't think there's anyone in secondary school, or maybe I shouldn't say only in secondary school, you can get a thing called a voltmeter, which would tell you exactly how much electricity is being produced. So look, there's things like, does this design work better than this design? Does the angle, you know, so it's, And to be honest, even getting them moving is really interesting for the students, like to see, even before you even go to electricity, to kind of come up with them and see them moving, because you have a lot of engineering and forces and stuff in that. So now stop, wait, let me just go back to this for a second so we can bring it all together, right? So this is where we went. So it's kind of always the thing with the STEM thing in the classroom is, where do you start? Because if you hit the students with too much information, it's back to that engage in the learning. It kind of takes away from what they're going to just experiment and try stuff out. So, but you kind of need to give them a little bit of information about how a turbine actually works. So what I possibly do, I would definitely, if you haven't fully covered all of the electrical...
Oh, sorry.
If you haven't covered all of...
I'm technical.
Oh, lovely.
Yeah.
If you haven't covered all of electricity...
I'm way out of... Yeah, I'm going to Spain.
Oh, lovely.
My mammy. So I'll be back midweek and I'll be up then.
Yeah. Well, listen, enjoy anyway. Yeah. Well,
yeah, just to...
Oh, lovely.
Yeah, it's nice.
Yeah. Girls, right.
Just the girls.
I don't know who's... So is that Fiona? It's not on mute. Sorry, Fiona, you've got no scratch yet. So sorry, I'll go back to this now. If you see there, like, so it's what we're looking at is the blade shape, the angle, and the speed. So the shape we talked about to maximize the airflow over it. So, is it better to have them, like what I showed, is the rectangular shape good? Is it better to have them pointed in a little bit at the end? Like, is it better to have them wider at the end? So how does that affect? Like, they don't know until they do it. The pitch is that tilting them to the wind that we discussed, that being able to tilt, and that's still like the picture there is exactly like the little hub that you will have, and that's the tilting it into the wind and stuff to be able to minimize drag and maximize lift across it. What you could, and I'm going to show you this, is that you can use, like, look, you call it design thinking, like it's a way to structure design thinking, or a STEM approach, that you're challenging them to build a wind turbine, test different blades and angles and the numbers of them to affect how good that means. Like, so that's the challenge, right? So what does using design thinking, like, what does that matter to you? Well, one, I'll send you the design thinking booklet that the students could fill in and follow. Like, you could print it. I don't think I have it, that you can edit it as a PDF, so you'd have to print it out, right? So the design thinking process, it's like the engineering process. It's just a methodology to follow. And what's really, really good about it is, if it doesn't work or doesn't turn out as expected to, so if it was an absolute disaster and you can't get any of the blades to turn, design thinking is built to capture that. Because that last bit there that says iterate means you go back in and you go, oh, what could I do differently? What about the design didn't work? What do you think I could change? Now, I think there's a big difference in setting young people up, whether it's primary or secondary, that like it actually can't work. Like, it would drive me mad, these recipes for slime everywhere, and there was an ingredient missed from it, right? So no matter what we would do in a classroom as a teacher, it wasn't going to work because it was fundamentally wasn't the right, like, ingredients weren't given. Like, that's very different, because that's like not designed properly or not given the right information. With this, the worst can happen is that the blades don't turn the way you expect it to, right? If that was to happen, the very worst, and the students take off the cardboard and they do have that corrugate underneath to have a look at. So the actual structure of it would be able to work. It just mightn't work as efficiently as they thought it would. So I think that's where design thinking or something is really helpful. It's not to be feared, right? There's nothing about it to be worrying about. If you wanted to use it, right, what it does is it's sort of like how we started the webinar this evening, right? So what you would do if you were going to use the design thinking and the design thinking little lab book for the students to follow, you would start by setting the challenge, right? So you would demonstrate, or that's where, as I said to you, that if I joined in a Zoom, I would set the challenge, because I would demonstrate some stuff about wind energy or turbines and how they work, and look a little bit around the blades. so you're setting students up first to kind of say, well, here's the problem, is that we really want that generator that's in it to turn really quickly. So if I want to be able to keep that turning, so I need to design something that catches the wind to keep that turning. Then you'd move into a research, so research is like find a little bit more out about it. So it's a bit like what we were talking about there, like that fast moving air over the wings, like you want to minimize drag, you don't want that to happen. So it's just like finding a little bit of information out. It doesn't have to be too now you don't have to do it this way. This is just as an example or a guide to be able to follow. Then you imagine, you come up with solutions, you come up with you might have a look at different designs or different ways that you might go, like what I said, fold the cardboard over, use one sheet of the paper and try different designs. The students might have materials that they want to check themselves. And then if you can, you draw out a little bit, you draw a sketch of what your design, and look, the sketch there, what ideal here would be the shape of your blades. What type of the blade shape would you go for? So would you have it just as a rectangle? Is there going to be an angle on them? Is there going to be that kind of trapeze look that I had there? So that's given, it's documenting how they're doing everything. And then you move to building it. So now you kind of have all that hard work done, and then you're going to move into building the actual prototype. You're going to build the model and have a look at it. And the final step in it then is you communicate. So you talk, you might, the students might, well, in some cases, go to Galway Science Festival and talk about what they did. They might stand up in front of the class or at an assembly and talk about their design challenge. But the big thing is that you iterate, you improve, you redesign. So someone next to them may have had a blade design that looked nicer, but didn't, they decorated it really nice, but it didn't spin very efficiently, where someone would have had a really nice, efficient blade design. So they could say, well, actually, because a part of it, as we all know, if we're design how it looks is really important as well, not just at the engineering part of it. So that's kind of where our creativity and communication skills come in. With you're not copying someone's design, that's going to be they're copying my design. It's improving your design based on what's went before, what scientists have found out before. So it's another way from a teaching point of view. Even if, so just say that you didn't follow this, and that's absolutely fine. That's what I'm saying, just totally up to yourself. But if you follow that kind of design thinking process or engineering design process, students have they've got really good critical thinking skills from that. And it's that really moving into that, what you want from STEM, that they're creative and collaborating. So if it doesn't work perfectly, the procedures worked really well. They understand why they were doing something and what they were trying to do. But look, as I said to you, that's me. So you might just build them this year and use that next year. You absolutely don't, you don't have to use it. So it's just the design thinking sets the challenge. So from my point, I'll stop sharing for a second. So back to what I was saying to you last week, was looking at that, that 5E inquiry model that I mentioned. So you're kind of building up to this design thinking challenge because you were engaging in some learning around electricity, even using the FET simulations or the transfer of energy, then moving into exploring that by constructing the little circuits, maybe testing for conductors, and then going back into FET simulations and explaining how it all works, that you've got electrons flowing around, and then coming to this bit, which is the elaborate, that you've gone into a bigger project that's using all those bits that went before to kind of apply that to a bigger project that you're going to do using design thinking. And the absolute final part of that is evaluating. And I suppose evaluate is more assessment of the learning. So that's would be more up to yourself. And if you were really, I suppose it's really important when you be going into secondary school with CBAs and stuff, that you're doing projects, it's just feedback on their project and what they did. When I think, I'm conscious of the time, and I know I go at 100 miles an hour. What I'd say to you is, everything that I explained there is in the notes. It's either in the PowerPoints or it's in the lesson plans that go with it. I do need to, I'm not going to send you, I'll send you the wind turbine one as soon as I can. I want to just update a couple of parts with this. Is a new, I've used this little hub myself, but I've never sent it out as part of a kit. So I don't think there's a picture of it in the kit, in the lesson plan. So I just want to update to reflect that, particularly for schools that weren't here. I think there's also actually, sorry, there's a certificate of completion of this program as well that you could give out, that they've completed the wind energy program and stuff like that. And I get, like, again, like, take it in pieces, like you take it in small chunks, don't jump into it all at once. I think the only little challenging, to be honest, the only little challenging part on this, and I think it's more of it, you probably have a better idea than me, is building the blades with a full class, like having enough. You kind of need to have a bit of sellotape and even some Pritt stick available if you were doing the fold in half design, like something like that. Well, like, I suppose there's nothing to stop you. If I'm only thinking out loud, if I folded that now, if I started that way, I just see. If I fold, I'm just having a look. I could then, once it's folded in half and it has a piece of corrugate, what I could do, I'm just doing it there as a talk now. I'd have to do it. I could alter it then and cut my blade aside. So one way you could do is that everyone starts with a rectangle and gets their little piece of corrugate on the inside, and then makes an edit and then alters their design. I don't know. I think I'd probably, before adding the corrugate to the inside, I think I'd come up with the design first. But look, that's up to yourselves. I wonder, have I missed anything, or do you have any questions? I do. This part doesn't really matter. Do you know what? I'm going to stop. I'll actually stop recording there now.